Today I'll be presenting the work done by the writers of the paper. 1 second. UniFormer, which is. Are you guys able to see my screen?
Yep.
Okay.
Yes.
So
I can see.
it works on taking the best of 3D CNN and transformers. My name is Aniket Ranjan, and I'll be presenting it today. So now this is what an input will look like when it is actually a video and not an image. It's basically a block of frames. So the input here is 3-dimensional, and so is the convolutional kernel applied to it. So even that is 3-dimensional. For a better outlook as to how it would look like in the terms of its working, so this is what the image says. So here we have a group of frames from a video, and here 7 filters are applied, and each filters are applied on a set of frames. So for each filter, there is a set of feature maps that we get. Then they are pulled and then sent to a classifier after flattening. Now, what does 3D convolution achieve? So this is a pictorial presentation. So here what 3D convolution would look like. And it's working on the first 3 frames, presenting the first feature map. Then it would work on the next set of 3 frames after working on the second and third feature map is found. So this is how it would rotate through the batches of frames that is sent. Now, so what does 3D convolution do best? So it captures the short distance redundancy. So 3 frames or 4 frames or n frames, which are there close by, adjacent to each other, they have certain redundancy, which is very local to that particular area. And 3D convolution can easily capture that. So I say this is temporal. Why? Because it is between different frames. But what it fails at is how it can capture the spatial information in the same frame. So it can look at the first corner in the first 3 frames, but it may not relate the same information to the rest of the tokens in the same frame. So this is where it lacks to attain much better spatial understanding, 3D convolution. Then what it has is another demerit is it has a very limited receptive field. What does that mean is the area through which the convolution can see among all the layers. So to overcome limited receptive field, the such 3D convolution networks have the requirement of very high, humongous amount of computation so that all the local learning can be aggregated together, and then a spatial understanding could be generated. Now, here is what a vision transformer would look like, which I'm sure many of you would be familiar with. So an image, this is just basically when the input is an image. It is basically fragmenting an image into 9 equal patches. It is fed into linear projection, flattened, then some positional encodings are applied, then a transformer encoder is applied on that. Through a multi-layer perceptron, some more processing is done, and then it is sent to a classifier. For a better understanding, let's say this is an image of a parachute in the air with some people. So it is fragmented into 9 patches. Then a linear projection is applied. So these blue blocks are the linear projections, then positional encoding is applied to a transformer and then classification. I hope this gives you a better picture. So vision transformer, it excels at spatial relations. Of course, it can take care of all the tokens in the same frame, but it will fail to relate to different frames. So like 3D convolution could take care of 3 or 4 different frames at the same time, but that would be a bit of an impossibility here with vision transformers. Not an impossibility, but it would be very hard. So they lack in terms of temporal understanding, and it is very data hungry. So to train the model, you need a humongous amount of data, and larger the data, the larger the training time and the computational requirement. So what we need to achieve is semantic segmentation. So here is that parachute. It is one of the 9 patches. But if I just directly, if the application is just a vision transformer directly, the amount of computation required to process the basket and the people in it, that alone takes a lot of time. And it also depends upon the resolution of the image. So the better the resolution, the more heavier the image, the heavier the computation. So this is one of the other demerits of vision transformer. Now, why the previous works haven't fared very well? So it can be attributed to spatial attention. So it focuses like 3D convolution, just 3D convolution models. It focuses only on neighboring tokens, but temporal attention where it takes care of adjacent frames, but not all the entities in the same frame. Now, we have another issue, which I guess I have hinted on in the previous slide, is that since the representation is very local, the learning is very local, to aggregate that, it requires even more longer time and hence high computation cost. Now, why we need UniFormer, like why the writer have proposed UniFormer. So 3D CNN gives temporal relations, vision transformer gives spatial relations, and if we combine these two best aspects, they give us UniFormers. So UniFormer is trying to get the best of 3D convolution and transformers. Now, here we have what the UniFormer structure would look like. It has 3 main segments. The first is a dynamic position embedding. So what dynamic position embedding does is, it will be explained a bit later. It's basically how different patches are encoded, the position is encoded. Then we have multi-head relation aggregator, the second component, and the third component is feed-forward network. These 3 are the main modules of UniFormer, but as per the writer, what they claim is the star of the show is multi-head relation aggregator, and I'll explain why they say so. Now, we have here some of the steps overview. So this is the input, what we get. Here, XIN is the basic input. Then we have the dimensions here. C is, it's like the channels. For an RGB image, it would be red, blue, green. Then here is basically very much dependent on the number of heads of the transformer. Then we have T, which is the number of frames, the height, which is the height of the frame, and width of the frame. The 3 main equations, which the 3 modules do, is equation 1 is dynamic position encoding. It applies on the input, and here in each of these 3 layers, they use residual networks, as you can see, a residual connection, xn plus x plus y. So in equation 1, it's encoding, giving positional encodings to all the tokens. In equation 2, it combines the positionally encoded tokens with contextual tokens, and it joins them, or it sort of aggregates them through token affinity learning. Now, what is contextual tokens? So this is what it would seem. We have an image. So contextual is basically, it's sensing the meaning from the image. So each segment of this picture is being fragmented and distributed in different colors. What does token affinity look like? So maybe you can say, this is not a very accurate example, but then I think it should explain how there are some 5 people, it is able to recognize the 5 different people here, and the cycles are very well recognized. So how token affinity work is, this is just for one single frame. It will have to relate to the next subsequent frames as well. So this is where token affinity comes into picture. Now, the third module, which is feed-forward network, it does a point-wise enhancement of different tokens. Okay, now we come to the first module in detail. So 1 second. Now, here we have the dynamic position encoding. It's basically very much dependent upon depth-wise convolution. So what does that mean is it applies layers of convolution on each of the frames as the convolution moves through the set of or the batches of frames. Yeah. So in why they propose the dynamic position encoding is when there is absolute position, it is limited by the length of the target video. So the training must have been done on certain length of a video, and if the testing video is a bit longer, then it needs to be interpolated between the training length, like to the training length. Then it does not use relative position because as they have researched that it hinders with sorry, I'm up to look at the question chats if there is a question. Yes, 3D indeed consume much memory. What is not a transformer? I suppose 3D convolution is definitely not transformer. I'll come to what transformer here does and how it is being applied. It is in the part of next module. Now we have so what they say is dynamic position encoding, embedding. It's an extension of conditional position embedding. When they proposed conditional position embedding, they said that they are using just relative positioning, but not absolute positioning. But in dynamic position encoding, they use both relative and absolute positions. Why? Because they do not use any padding. When padding is not used, the edge patches, the corner, the patches which are at the boundary, they themselves are used as absolute position. Then for relative positioning, each patches communicate amongst each other to understand what how close or how affine they are to each other. So as you can see, the tokens self-encode via local querying. There are some benefits of dynamic position embedding. The first is no padding is used. As I said, it's a simple 3D convolution. Very important point is they are not permutation invariant, and it is a very good thing. We do not want a permutation invariant. We want permutation variant, not invariant. Why? Because if suppose different pixels or different components of an image are changed, then the system should identify that, and it should tweak its accuracy, its performance accordingly. It should not just be, it should not assume that different components or different features within an image have certain relationship. What translation, it is also translation invariant, which means that when different images are moved, suppose there is a video of baseball swinging, the baseball position relative to a same frame would change. It would, from top to bottom, it will swing. But then the system is it should be able to identify the bat. So this is what is mean by translation invariant. And as it is border self-aware because of no padding, because it uses absolute positioning for edge patches. Now, here comes the meat of the section, which is MHRA. It stands for multi-head relation aggregator. I'll say our relation aggregator for short. But relation aggregator, when it comes, when we are talking about just one head. Now, MHRA brings two things together. The first is a 3D convolution and spatiotemporal self-attention. What temporal means, so as I have said before, that 3D convolution takes care of the temporal aspect, and transformer takes care of the spatial aspect. So as it is temporal, it resolves redundancy, local redundancy, and spatial attention, it resolves global dependency. So this is what the writers profess, that this is what differentiates them or their model from the others. So the steps are, we have an input, as you have seen before. it is changed into a sequence of patches or sequence of tokens, not patches, sorry, sequence of tokens. Here L stands, it's like the number of patches. So it's basically the number of tokens is basically a multiplication of the number of frames, the height and the width. Now here we have the main set of equations. What happens in MHRA? The first is to the input X, we apply a linear transformation, Vn, and I'll explain sequentially what they mean. So Rn here is a relation aggregator, and n, the small n, refers to the n head. There are capital N heads, and small n is just one head of the capital N heads. So this is a relation aggregator. An here, I'll explain what this is happening here. So An here is the affinity matrix, which takes care of the global relations in one head. Vn is linear transformation for the nth head, and U here is a learnable parameter which learns local relations. So what is happening here is it's taking the input X, then it applies a linear transformation, which is V here. Then it applies, when it sends it to affinity, it multiplies it with the affinity matrix. This is the result for one single head. Now, in the next equation, which is equation 5, it concatenates all these n heads and capital N heads output, and it takes a dot product with, it multiplies it with the learnable parameter matrix, which I just said, which is capital U, taking care of local relations. I'll explain how affinity is taking care of global and local relations, but U here is taking care of the local relations. And the main pivot here for the whole model is the matrix A. So we have MHRA. It has a local segment, which is local multi-head relation aggregator. Between batches of frames, it takes care of the relations between different tokens. So here they take a detailed feature through 3D convolution. Here omega I represents a neighborhood, or as the paper says, a tube. So imagine you have a neighborhood, it's a block, and in that neighborhood you have one house, and you want to make similar, like how similar the people are, how similar the houses are. So you have to do that. So omega I here represents that neighborhood I. And why is it I? Because there is an anchor token, which is xi, and all the rest of the tokens inside this neighborhood will be xj. So what is this equation doing is, it will be shown in the next slide, because I wanted to keep things very particular over here. So I'll come to equation here, equation 6, in the next slide. Now, you can see the dimensions of an, small an. Then a relation aggregator is applied after local affinities obtained. What you can see here is when this V is applied, the linear transformation, it's a pointwise operation. When affinity is applied, since it takes care of many different frames, it's more like a depth. So it's like depth-wise convolution. Then when you multiply it with U, as you have seen in equation 5 in the last slide, that is a pointwise convolution again. So this whole sequence is like a pointwise, depth-wise, pointwise convolution. The resultant is fed to feed-forward network for better representation. I'll come to the questions. I see there are some questions. I'll come to the questions after the slide, sorry. Now we have the second segment of MHRA, which takes care of the global relations between all the frames in a given input. So what it looks like here is, now we are moving here from 3D convolution to transformers. We have the neighborhood, which is the capital omega. And here they have used this equation to calculate the affinity among all the frames tokens, all the tokens inside all the frames of this particular batch. Again, xi is the anchor, xj are all the neighbors. Sorry. Now, one very particular thing, and how they are drawing an analogy between transformers and this model is they say that the linear transformation here, Q, the K, and here we saw V. So they are very analogous to the query key and value. The three, when we see self-attention, so we have seen query key and value. This is what they say is very analogous to. Because of dynamic position encoding, it remains permutation invariance. It resolves permutation invariance, and it holds translation invariance. I have explained this in the previous slides. One benefit through DPE is that it makes a test video length more flexible. It's not very rigid compared to what, depending upon what the input video length was. Here, this is where the affinity is being calculated, as I had said. So this is a continuation from equation 6. So in equation 6, 9, 10, and 11, they are calculating the indices of every single token in the neighborhood omega I. Then equations 12, 13, and 14, it's making a check as to are the tokens which are being considered or being matched within this neighborhood or not. If not, then the affinity value for that particular token would be 0. And for the rest of the tokens within this neighborhood omega I, so equation 16 is how they subtract between the affinity of I and j. I think this is a learnable parameter for them. In the feed-forward network, it's very simple. Like any feed-forward network, 2 linear transformations and 1 nonlinearity introduced. The peculiarity here is what nonlinearity they have used. They have preferred GALU, that stands for Gaussian error linear unit. Some features are like it does pointwise operation on to enhance the representation obtained from the previous layers. It combined linear transformation with nonlinearity, and then again it feeds into a linear transformation. The main benefit of GALU is that it gives better gradient because it has much more refined curvature compared to ReLU. You can see from the image here that ReLU is very straight, but GALU, the blue line, has a little bit more curvature to it. So the gradients are much better when the weights are updated. But however, they have proven that asymptotically ReLU and GALU are same, but and it is monotonically increasing. So I think these are the benefits they're trying to sow from this nonlinearity. Sorry, reap. Okay. Now we are moving to DPE kernel. So I'll come to the famous image of what the architecture looks like, but then I have taken the liberty of positioning according to how I'm moving the information through the slides. So that will come a bit later. So we have the DPE kernel. So for the positioning, the depth-wise, we employ 3 to 3 into 3 encoding. Then for stage 1, the convolution filter is this. I'll accelerate my speed because I guess I'm very slow. So here the convolution filters are this before it is fed into stage 1. This is very important. This is just for the depth-wise convolution. Then for other stages, it does point-wise convolution through 1 into 2 into 2 convolution filters. And since here is here it's much more deeper, so it's depth-wise convolution. Now, the next is, this is a transformer-inspired model. It is very hierarchically stacked. There are 4 stages. As I have said, the sequence is a bit ambiguous, but then sorry for that. So here we have stage 1 and 2, which counts for local affinity. The head count n is the same as the channel size, as I've said in the previous slide. Channel 3 and 4, they look for global affinity, And here they have fixed the head count to 64. The variable channel sizes for local affinity are 64 are these. And the variants are based on the number of blocks stacked. So small is this, and the big one is this one. So the local neighborhood, as I said, the tube, which they say is 5 into 5 into 5, 5 into 5 into 5 tokens. For the local MHRA, they use batch normalization because that gives better gradient. And for global MHRA, they basically use layer normalization for much more refined features. Then they send the whole resultant to average pooling, then apply the feed-forward network. They have used the feed-forward network expansion ratio, which is 4. And what it does is, it's like magnifying or zooming into the decision boundary created to understand much more clearly as to how the decisions are being made for each data or each data units or each particular token. Now, this is the famous picture which you might be waiting for. So here is a set of frames being sent. The convolution, as I said before, is a depth-wise convolution being applied. Then it's being fed to stage 1. So you can see how this sliding window is affecting, how the strides for depth-wise convolution is affecting, and the strides for point-wise convolution is affecting. All these point-wise convolutions happen after it has been fed into stage 1. So it moves, as you can see from the picture, and each stage is basically a sequence of depth-wise convolution, then a residual network, a normalization, then, as I've said, the linear transformation, V, then multiplying it with affinity matrix, concatenating it together with, and then multiplying with U. So this is all happening in MHRA. The same applies to local and global MHRA. Then again, a residual connection is applied, normalization is done, and the feed-forward network. And as I've pointed it out, it's using GELO. Okay, for the data set, it's using kinetics 400, kinetics 600. They're basically data sets where a human is doing any sort of task, any sort of movement, but it is not predefined. But in something version 1 and 2, it's whatever the tasks or whatever the video is showing is based on a predefined set of tasks. I suppose something is much more organized compared to kinetics. So for the training, they do dense sampling, and for kinetics, and uniform sampling for something. For testing, they use both the data sets. So coming to the results and performance, they do see like huge computation drop of 42,000 gigaflops. And for the 16, the smaller version, the improvement is just 1%. But for bigger one, the improvement, I don't think they haven't given a number for it. And it seems they say that it's comparable improvement. So I suppose there is less than 1%, I suppose. Something they achieve for the bigger model, 32 version, the accuracy of 61% on version 1 and 71% on version 2. They did an ablative study to understand, okay, they did an ablative study. So here they found that their model works better than mobile net, and feed-forward network does indeed refine the representation. Then they have sort of summarized their conclusion compared to what previous works have done, saying that attention is best learned jointly, like local and global, like spatial and temporal attentions. Then it learns many different representations, which much less work, and hence the transfer learning is much better. Some notes. So due to dynamic position encoding, the improvement in performance is not much, but they say that it's 0.5 to 1.7%. It's good for representation. Now, very important here is, as you have seen, that there are 4 stages. When all the stages are local MHRA, the accuracy drops, the performance drops. Of course, there is a very significant drop in number of computation, but the trade-off here is shouldn't be in favor or tilting towards a number of computation, much so compared to accuracy. But when they put all global MHRA, of course, it can be imagined. It is very apparent that a computation cost would soar at much accelerated rate, but to our surprise, the accuracy does not increase. It also drops. So the best choice they have found is the first two stages should be local MHRA, and the last two stages should be global MHRA for local and global attentions, or spatial and temporal attentions, to say. Joint attention is best for transfer learning. They have proven that. The tube here is 5 into 5, as I've said. The training sample is sparse and test sample is dense, of course, and these are the number of frames and the strides they have chosen. They have clearly mentioned in many different places on the paper that they're sort of trying to balance the performance and efficiency trade-off. So this is what the smaller model, the smaller version, B16 version, does for them. They show that here they have, for number of floating point operations, for something version 1, what is the, and they say that top one is basically when your prediction is the top prediction, the correct prediction. So the higher it is, the number of times you give correct prediction, the better your model is. So this is what they say, the bright pink is their model. But I found something, that they indeed are not the best as they claim, because recently on the same top 1 and top 5 something dataset, sorry, kinetics dataset, they are at position 5. This remains same, the accuracy remains same, and but then they here in the graph they have said that they are on the top, but then somehow it feels that they are not. Regardless, so as I've said, top 1 means correct prediction, top 5 means your prediction is in the top 5 options. So these are some of the informations which are in the paper. I'll have to rush because I'm taking a lot more time of yours, so I'm sorry about that. These are basic information on sampling and what is the number of operations, the accuracy for different data sets and clips, what they try to include and what they don't include. Now, this image you would have seen in the paper. So as you can see, but if the input looks like this, it's a set of 12 frames. Sorry, how many frames are there? Sorry, 16 frames, I suppose. But for 16 frames, when you have LLGG, as I said, this is what they have chosen as the best. The task here is to identify hoverboarding, and the focus is very precise here, as you can see from these two blocks, these two tokens. It's very precise over here. But for all local, it seems that it's focused at somehow, but then it's not very precise. And for all global, it seems it's scattered all over the place. So that's why they have chosen first 2 local MHRA and the last 2 stages are global MHRA. Now, do you think that this is the end? Possibly not, or hopefully not, I suppose. So we have some live demos, indeed. So I'll visit here. Instead of showing what the writers have done, I'll try to include some of what I have done. So here is a video of a person running. And I submit. So this is what the video is. Here you can see that it's saying lunge, triple jump, high jump, but somehow javelin throw is also coming. I think it's probably because of the streaks. These are coming in the image. Now I'll show with something else. Here you can see it's a bit more interesting. A video, I suppose. So it can correctly identify that they are jogging. Sorry, it's taking a bit of time. There's a group of people who are jogging on the road. Now, for this one, I tried to input a very non-familiar task, but the accuracy is quite good. We can see that the lady here is doing yoga, stretching legs. So they have high accuracy for that. So this is the leg stretch video. So it's able to identify yoga and stretching legs with almost equal precision. For here, I set an example of bat, swinging of the bat. So it should be able to identify. So when I submit it, the bat was swung here, and it's saying playing cricket with very, very high precision. So here the decision is very clear about it. The last one, a bit more interesting, is this one. Here is a singer. I suppose you're familiar with her. She's Adele. She's performing. Sorry, it's a bit heavy video. It's very high quality, and it clearly identifies that the accuracy is singing. Just a moment, and you can see her singing yourself. So it's basically singing. I'll attend to questions. Sandro X. There is a video. I'm not sure why is it not playing. So yeah. So I'll wait. I'll stop that. So here, I'll come to the questions. Sorry. So if you have questions, of course you have, which I'm coming to. Yes, the start comes first because the video is very heavy, very high quality. And since I'm on call, there are many applications running, so probably the latency because of the Zoom call. Now, what is XN? XN is the input input to the first layer. So you can take input as here is a set of frames, which is then segmented into different tokens. Okay, local features are object. Global is the entire frame. That is right. The local features are local relations are basically the features or the objects in the image. Global are like how the objects is being translated throughout the frames. Am I not audible?
Yeah, you are audible, Aniket.
Okay, someone said turn on the sound. Thank you.
Maybe the video he's talking about.
Oh, so do you want me to play the video? I can play it. Okay, so as you can see that there is a tremendous latency. When I was testing it, there was no latency, but this is a very heavy video. It's a very high resolution. So probably that is why. Relates each frame. That is right. Transformer relates each frame. That is like it's aggregating all the locally learned information through affine matrix, which is through local MHRA, and it aggregates through all the frames within a batch or within a video to have a much more clearer global understanding. Any questions? If I have not addressed any, please let me know. Any questions you have?
Aniket, I have a question.
Yes, of course.
You explained well, actually, really well, but I didn't understand quite. What does a head means in the VNX? You know, as the part of RNA, they have something like a V underline N and X, which n is the number of head, or
that is right. So you know that in transformer model, there are heads, different heads at play. Why? So that is called as multi-head attention. So in multi-head attention, so what different attention heads do is, for the same input, they're trying to learn what the input means in their own way, very randomly. So somehow, if like it's like a teacher teaching a group of students in a class, not every student learns the same thing in the same magnitude. So everyone grasps different components. So this is the intention of multi-head attention over here.
That's why they call it multi-head. So
that is why they call multi-head.
Each head has different weights. Okay. And
Correct.
it's going to be learn different weights. Good, nice.
You can see that in equation 6 of the paper. Sorry, equation 5 of the paper.
I saw. Yeah. I think there was it. Yeah, if you show me that again.
Sorry. Yes, I can come to that. Okay. Let me come to that. Sorry. So I suppose it's here. You can see in equation 5.
Yes.
So this small n refers to a single head, and capital N refers to n heads, all the heads. And where does this n value comes from? These are the number of channels. And
the big N is the number of channels.
The number of channels.
It makes sense. Okay.
And the channel numbers are 64, 128, 256, 512.
Yes, 64. Yeah. Good. Oh, now I understand. Okay, the N goes from 1 to capital N, and it will be learned by different weights in each head. Good. Thank you so much.
Oh, good.
Really good presentation. Really good.
Thank you. Any questions you have?
So Aniket, is there any pre-trained version that can be used for any kind of transfer learning in future, or we have to do it from scratch?
I think there are many versions, many different models which you can use for transfer learning. Definitely. I think last year they one of the transformer models for visual competition was Swin transformers. I'm not sure if you have heard of it. The Swin transformers also works very similar to this one, which I have just presented, UniFormer. That is, I guess, it is a pre-trained, so maybe that can help you.
Okay. So in this, when the author has said that they have experimented using ImageNet 1K image classification, so they are doing it from the scratch, or they are using something which is pre-trained?
I think they have used a different model during the ablation studies, and that was, I think, MovieNet, or I'm forgetting the name, sorry. I think they have said that it's a MovieNet, possibly. I can look for the name. In the ablation section. It's not at the top of my head at the moment. I've forgotten the names.
Oh, it is in the paper, right?
It is in the paper. Yes. Give me a moment. Let me have a look.